Hello everyone, welcome to In 5 Minutes. In this video clip, we will continue with the questions that were asked in May June 2015 paper. The next question in the first compulsory question number 1 was based on Norton's theorem. The question says, for the given circuit, find the Norton's equivalent between points A and B. So there are 2 points A and B across which we have to find out the Norton's equivalent of this entire network. So let us follow the steps that we have discussed in finding the Norton's equivalent circuit. If you remember, Norton's equivalent circuit is the one in which we have a current source connected in parallel with the equivalent resistance, which we call Norton's resistance, but it is exactly same as the Thevenin's resistance in its value. The value of the current source will be called Norton's current, or it is also called short circuit current. So let us start with step number 1. In first step, we will find IN, which is Norton's current, or ISC, which is short circuit current. So when we find Norton's current, we will have to remove whatever is connected between points A and B. So in this case, RL is connected between points A and B, so I'm going to remove RL. And I will draw the rest of the circuit which I have done. This is 10 volts battery. All 3 resistors are of 1 ohm. And now, between points A and B, because we want to find short circuit current, we will short points A and B. So we have 2 points defined A and B, but we have short circuited them, and the current through this short circuit branch is called ISC, or it is called IN, Norton's current or short circuit current. So let us find out ISC or IN in this particular case. We can use variety of ways. We can use either mesh analysis. If I want, I can use nodal analysis, or one can go for the simplification of the network, find out this I total and then use current division rule, etc. So I'm right now doing it using nodal analysis, in which we will be applying KCL at node X where the voltage is Vx. I will consider 3 outgoing currents. The first current is going to be Vx minus 10 divided by 1. This is the current, Vx minus 10 upon 1. The middle branch current will be nothing but Vx upon 1, and this current will be again Vx upon 1 equal to 0, because there are only 3 outgoing currents and we have not taken any other current. You can see the denominators are all 1, so we get 3Vx equal to this minus 10 goes on the other side, becomes plus 10, and therefore Vx is nothing but 10 upon 3. Once I know Vx, which is 10 by 3, I can now calculate ISC or IN. That is because ISC or IN will be equal to, it is a current through this branch AB, which is also the branch carrying 1 ohm resistance. So this whole current through 1 ohm resistance will be nothing but Vx upon 1. So IN is nothing but Vx upon 1, and that means it is exactly equal to Vx, which is 10 by 3 amperes. So we finally say that IN is equal to 10 by 3. So that was my step number 1. My step number 2 is going to be finding the Norton's resistance Rn. I keep saying that Norton's resistance and Thevenin's resistance are exactly same. They are found also using exactly same approach. So to find the Norton's resistance, we will once again draw the circuit, but this time we will have to replace the sources. Voltage source will be short circuited and current source will be open circuited. There is only one voltage source in this case, so that voltage source will be short circuited. The rest of the circuit will be as it is. So we get 2 points A and B, and this time, because we are finding out the equivalent resistance between A and B, we keep them open and we define this resistance as Norton's resistance Rn. So you can easily make out that these 2 1 ohm resistors come in series, come in parallel, and the parallel combination will be in series with 1 ohm. So if I now define Rn, my Rn is equal to 1 parallel 1. These 2 1 ohm resistors are in parallel, and that will be in series with 1 ohm. Parallel combination of 1 and 1 will be nothing but 0.5, and therefore we get Rn equal to 1.5 ohms. So that's my second important answer that I was looking for. We will now go to step 3. In step 3, we will finally draw the Norton's equivalent circuit. So for Norton's equivalent circuit, we first take the current source, and in parallel we take the resistance. The Norton's current value IN came out to be 10 by 3 ampere. and the resistance Rn came out to be 1.5 ohms. These 2 points will be nothing but A and B, across which we have found the Norton's equivalent resistance, Norton's equivalent circuit, and now we will bring back the originally connected resistance RL across A and B, which was of value 2 ohms. So this becomes my Norton's equivalent across points A and B.